So welcome you to another session in Frontiers in CFD. Today we will see the CFD simulation of prismatic cell lithium-ion battery pack. So the first objective is preparation of geometry of prismatic cell lithium-ion battery pack, generate mesh and name selection on computational domain, applying the boundary conditions and visualizing the result. So this is the specific specification of the geometry for the lithium-ion battery pack. This is one which we are going to follow. So it is a prismatic shape, 100 mm, 220 mm and 145 mm. So all the dimensions are in mm and we are following the same specification. So this is in detail related to the specification of geometry for the CFD simulation of prismatic cell lithium ion battery pack. So there are total 12 cells. Each of them are separated by 5 mm as a distance. Then as I said earlier in the previous slide, the dimensions are 100 by 145. So the whole pack is of 320 by 105 mm. Prepare the geometry of prismatic cell, which is used in lithium-ion battery pack. So this is all the dimensions which are given in mm. So accordingly, we are going to prepare the geometry in design modeler. So we'll open the new design modeler. Set the units first, that is mm. So let's have the units mm. Click on the any one of the plane. So first of all, either you can create the box and then you can proceed with the other. So 320 by 105. So this is a box dimension I will prepare. So create primitive. This is a box. So X component I will take 320. This is 105. So as per the this one 320 and 105 we are taken. So make it add to frozen. The height will be here. So let's follow the okay. So this is the height will be 145. So accordingly we'll take it y component 145. So now this is how the geometry that is prepared. Let's make it generate. So now this is the first cell. It is 20 by 100. So one more time, go to the create, select primitive box. So this is x component is 100, z component is 20, this is 145. Okay, so right now the box is somewhere here. I want to shift it by x coordinate, that is equal to 5. So you will see here. Similarly, I will shift z coordinate, that is equal to 5. Instead of add material, make it slice material and generate. So this is the first cell which is generated. Second cell will be at a distance of, this is 5 plus 100, 105 plus it is 110. So create one more time a box. Now x coordinate, here x coordinate is 100, y coordinate is 145, z coordinate will be 20. Now shift the origin to, so it is 100 plus 105 plus, so it will be 1110. Shift z coordinate by 5. Instead of add material, make it slice material and generate. So this is the second cell which is generated. Same way, go with the third one. One more time, box x coordinate, here it is 100, this y coordinate is 145, z coordinate is 20. Now shift in x direction, so that is 100, 200, 105, 1110, 215 in x direction, z direction. Make it slice. Let's generate. So this is the 3 we have generated. So one more time, create a box. Instead of add material, make it slice material X coordinate will be 100, this one will be 145, this will be equal to 20. Shift X coordinate by 5. Now Z coordinate will be, first it was 5, then 20, so 25 plus it is 30. So here it is there. So make it generate. So now the second cell is generated. So create one more time the primitive. Let's say box. Make it slice material. X coordinate will be equal to 100. The Y coordinate 145. This will be equal to 20. Then shift the X coordinate by the distance, that is equal to 100 plus 1 5 plus 5, that is 110 here. So shift Z coordinate by 5 plus 20 25 30, let's say here. So now make it generate. So this is the second one. So one more time go with the third one, say box. So this is X component is 100, Y component is 145, Z component is 20. Shift in X direction. Now X direction 100 200 plus 5 plus 5 10, so 215. In X direction Z coordinate will be again will be equal to 5 plus 20 25 plus 30. So let's take it 30. So make it slice material and let's generate. So this is the two rows we have generated. So one more time create primitive, say box. X will be 100, Y will be 145, Z will be equal to 20. X coordinate here is 5, Z coordinate will be 20 plus 40 45 50, and this will be equal to 55. So it will be at location. Make it slice material here and generate. Similarly one more time take it box. X coordinate 100, Y is 145, this will be equal to 20. Then X coordinate will be equal to uh, this is 100 plus 5, so 110. X coordinate, Z coordinate will be equal to 30. Let's see here. So 20 40 45 50, and this will be equal to 55. Let's see here and make it slice material and generate. So let's do this last one. Create box, say 100, this will be equal to 145, this will be equal to 20. So X coordinate will be now 200 plus 5, 21 plus 5 210, so 215. In X direction shift it the Z component as 20 40, then 45 50, and then this is equal to 55. So it will be at the third place. Make it slice material over here and generate. So this is the third row we have generated. One more time the last row, that is box. So X component is 100, Y component is 145, Z component is 20. Now X component will be, this is 5, Z component will be 20 plus 40, 20 plus 20 plus 40 plus 60 65, then 70 75, and this will be 80. So it will be at this location. Make it slice material and generate. So create one more time the primitive as a box. Say this is X is 100, Y is 145, Z is 20. Show X coordinate will be equal to 20 plus 100 plus 5 105 plus 5 110. So Z coordinate will be equal to this is 20 40 60 65 70 75 85. So 80. So this will be at this location. So make it slice material and generate. Now last one, create box. X is 100, Y is 145, Z is equal to 20. This X coordinate will be 100 plus 100 200 205 210 2115, so 2115. And Z coordinate will be equal to this is 20 40 60 65 70 75 80. So it will be at this location. Make it slice material and generate. So ensure that all of them are sliced. So this is solid, 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 solid. And last one, this we need to make is a fluid, because this will be the zone where the fluid is likely to flow. So I will change the name of this to say battery pack. This one you can name as cell 1, cell 2, cell 3, say cell 1, or we can write prismatic cell 1, prismatic cell 1. Similarly, you can write this as V cell 2. Same way you have to do it for all. P cell 3, cell 4. This is just for understanding the location, understanding the which part is there. So last, this is P cell 6, P cell 7, P cell 8, this one P cell 9, this will be P cell 10, this one will be P cell 11, and last one will be P cell 12. So now what I will do is I will make this as a new part, so that I don't have to put many boundary conditions in the latter setup. So I will rename this again as prismatic cells. So this is a new component which I specified, and later on we can proceed with the setup as well as we can do with the applying the boundary conditions. So we have already prepared the geometry as per the specification in the previous slide. So this is how the 3D view of the prismatic cells. So you can see this is your battery pack, which is considered to be a fluid zone. Then your prismatic cells, which are been provided here. So they are been specified as a solid. So from starting from cell 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, each of them are considered to be equal to solid, and only the battery pack where the fluid circulation is taking place is been mentioned as the fluid. So based upon this, we are going to prepare the further things. So geometry has been prepared. Some basic operations are been done in while preparation of geometry. Uh, some boxes been created. Then the respective boxes are created for your the prismatic cells. The dimensions are as per the specification which is done in the previous slide available here. So let's proceed with the second part, that is related to your mesh. So make it open. Okay, so the mesh has opened. I will just first generate a default mesh and see how the mesh look likes. So it's not as per the expectations, so we're going to make it slightly finer one. So if you remember, our dimensions was 5 mm, so accordingly I will put it say around 0.02 first, or let us say 0.01, and we'll first generate it and we'll see how it goes out. Okay, it slightly becomes better. So 0.005 will make it. Let's make it generate again. Okay, it's now become slightly better. But we can, let's look for something 0.02, let's say, and let's make it generate again. It will be slightly finer than that, but again the time required for the mesh generation will be slightly higher. So this looks to be a better one. I'm not going in much details of the higher, uh, we can say, more finer size, because the time required for the simulation will be considerably more, and based upon that we're going to follow this one. So it's time to specify the inlets and outlet. So this will be your outlet. This we are going to specify as inlet. Okay. Now we'll just hide the geometry of battery pack, and we'll define the cells wall. So we need to select all the cell walls. So always check for something which is left. Okay, so almost all of them have been selected. So define this as so let's okay, so we have on it. So this is your battery pack and this is your cell. Okay, now next thing is make it update. You will see the mesh translation to Fluent successful message. Once this is received, you can close the meshing option. Let's go with the setup. Depending on number of processors you have, you can set it. So I'm putting it around 10, double precision. Let's start the process. So this is how the geometry will be loaded. So specify the gravity minus 9.81. Why minus 9.81? This is positive direction, so it should be in the degree below. So transient I will specify. Model here, the multiphase model, we are not turning it on, only we are turning on the energy equation over here. In case of viscous, I will select k epsilon. then enhance wall treatment, thermal effect and curvature correction. So all these options are selected. The next thing is selection of material. So if you want to keep air, you can keep it air also, or if you want, you can select the water as a working fluid also. So if I selected water as a working fluid, I will close this. Then instead of the solid which we have, so I can select the material which is required for your. So normally is the nickel is been coated with it, so you can select that option. So make it copy, then close it. So you have the option available. So this is all related to material. Then go to the cell zone condition. I will keep it as it is. In the boundary conditions, you will be observing some regions over here. So on the cell walls, you will be having some boundary conditions which are been available. So accordingly, we'll put the thing. Uh, Specify inlet. So that will be the flow velocity which we are considering. So let's say velocity magnitude is 1 meter per second. Let's make it apply and let's close it. Nothing we are going to specify at the outlet zone. We'll be dealing with only with the inlet. So all prismatic cell. So I will put the boundary conditions over here. You can apply heat input also. So at each and every place you need to put it the wall condition. These are the boundary condition which you are specifying. So 323 Kelvin means around we are putting it 50 degrees Celsius. Okay, so we applied it at each and every location. Now let's proceed with the next part. So reference values, again we need to tell the computer from where to start. So we'll specify this is inlet here. Here it is battery pack. Then go to the initialization. Again we need to tell it from where to start. So it will be inlet. Let's initialize. Then go to the calculation activities. Let's put this some value 20 here. Solution animation. So new object contours. I need to observe temperatures. So say total temperature. Now where I want to visualize inlet, outlet and wall. So I have selected all these three. Go to the color map option. Instead of exponential, make it float. Close and make it save display here. So if you want, you can specify the name also. So this is the first thing which I am taking is total temperature. Make it apply. So if you want, you may add another one, new object, contours. Instead of total temperature, if you want, let us say a static temperature, you can use that. Inlet, outlet, and this is your wall. Go to this optional, make it float, make it apply, close, save display. You can close this. This contour too, you may specify it as static temperature. If you want, you may enter the velocity also as a contour. Make it okay. Go to run calculation. Instead of fix, I will go with adaptive time step. Say first of all, I will run it for 100, and let's take it around 0.5, and let's do the calculations. So calculation will take some time depending on how much flow time you want. So I had just taken it for 100 time steps. So accordingly, it will proceed. The animation window will also open. Okay, that you can see now. The temperature distribution is been visible over here. So these are the two things. One, it is contours of total temperature. If you want, you may visualize in some other way. This was your inlet, this was your outlet. So we have to wait till the time the calculation is completed. So we have done around 1400 time step. The flow time is around 1.11 seconds. Now we'll save the work and visualize the result section. So let's save it again. You can close the Fluent window also. So let's edit. Okay, let's open the volume rendering. So, so if you want to visualize temperature, select the temperature. You can specify the user specified temperature range, the one which we have specified. So let's take it, make it apply. Just a minute. So this is the volume rendering. You can increase the resolution so as to visualize in better way. So resolution right now it is 100. So it is as per the temperature we have specified. So this was your inlet and this is your, on this side it is your outlet. So let's see the another contour also. Let's say velocity. So volume rendering 1. So I will make it to around 20 just to visualize. Okay, so this is your inlet and this is your outlet. You can, so higher resolution will give you, okay, 150. So this is for higher resolution. So let's visualize the second one. Make it 150. So you can continue the simulation for further more time by running it. So let's go back to workbench window, save it. In addition to that, you can have the variables, you can have some text option, time step, location, let us say center, top, you will see here. We can have flow time also. You can have time value, location, let's say left bottom, so you will see time value. This legend you can shift it some other place, left, let us say center. So this one can be reduce. Instead of scientific you can make it fixed. Precision you can change. Okay, if I take it 2, so it will be like this is volume rendering right now. Make it apply. Then you can add the file date also. Say file date, location, let us say left and top. Okay, so likewise it can be done. So this is one of the contour. Let's You can visualize the contour for some more number of time step. So you can run it again, let us say 50, and continue with the further iterations so as to visualize it for higher flow time. Right now the flow time is 1.11, so you may want it to be more than say 10 minutes 600 seconds or something in order to compare the result with respect to the experimental one.